In part 2, we are going to again take a tour on common keywords you would find when you study when you talk about numbers. So let's jump right into it. So first of all, you may have seen or have heard these words already. If that's the case, then good job. If not, then don't worry. I'm gonna take a recap. I give you the definition and some examples on how these are used. When you talk about numbers, usually the first few concepts are divisibility. That's a long word. Divisibility. And if it's not divisible, then we need to find the remainder. Then numbers can be separated into two groups, like a prime or a composite, which you see again shortly, and then we can factor a number and express a number in a different way. Then some keyword on square cube or power of something. But there are like 5, 6, 7 keywords. Let's jump right into it. First one is divisibility. It is asking whether a number can be divisible, can be divided by another number. Given two numbers, m and k. Oh, sorry, given two integers. This we need to use the word integers here. And we say that m is divisible by k if we can write m as a product of k and another integer. And we can divide them. In other words, we can write m as k times n, integer n. Again, this word is important. Right? N needs to be an integer because you see, when what happened this is not. And there are 2 or 3 things. First, we denote that in this notation. We don't use this a lot, but again, just in case. Then but the better way is to just write it out. K divides m. Done. Right? Or as you can see up there, that's one way. Or you can say m is divisible by k. Notice that the row changes. K divides m usually means m is larger, and then you use k to divide, to make them into smaller parts. But on the other hand, m is divisible by k. M is something large. It can be divided and is divisible by a smaller number. Oh, there's another one, which is k, the factor of m. We discuss the concept of a factor in a moment. For now, that's the definition. And maybe there's a numbers, that's hard to see, right? But imagine you have a block of size 21. You have a number 21, let's say. One way to think about that is as dots on people or points. So you have 21 balls lying around. Right? You want to divide that into smaller groups, smaller groups, balls. And one way you could divide them into groups of 7. That's 7, that's 7, that's 7. So that's 3 groups, and each group has 7 balls. But that means we can divide 21 balls into 3 groups. That's the intuition behind the word divisible. And the more visual one is to arrange them in squares. Oh, sorry, in rectangles. So if you have a number, if you can arrange the numbers or the dots as a rectangle, then you can divide them by either side. In this case, there are 3 rows, so you can divide that number into 3 groups. Each group is represented by a row. You can divide them into 7 groups. If you divide them by columns, divide them into 7 groups of equal size. Oh yeah, I should have said that. They have the same size. There are 3 balls in each group. So that's the intuition behind the divisibility. And the next question you may ask is, what if you can't? Let's say you have an extra ball. There are 22 balls now. But that means you cannot divide them. And you cannot divide 22 by 3 or 7. A shorthand notation would be 3 divide, but then you cross it out, just like you cross the equal sign to say it's not equal. You can cross out the division symbol or the divide symbol by cross out to indicate that 3 doesn't divide 22. If it doesn't divide, then we have to, then there's gonna be some leftover. Think of it visually up there. If you try to arrange 22 objects into 3 rows, you can almost get there. Almost get there, except you have one leftover object. And that's what we call the remainder. What remains after you divide them. Remainder. In this case, it has a remainder of 1. 22 objects divided into 3 rows. Each row has 7 objects, and there's 1. There's a remainder of 1. Those are the 4 numbers you get. But what you are given 2. You are given how many objects are there and how many groups you want. Once you settle these 2, then the number of objects in each group is fixed and the remainder is fixed. And there's only one way to divide 22 objects into 3 rows, into 3 equal rows. Have one leftover object. But actually I was lying a little bit because there are more than one way. And you can say, oh, what if we, just take these 3 out and make them remainder as well? In this case, you will have what? You have each row will have 6 balls, and the remainder is 4. So there are more than one way. But that means we have to, but that's not natural, right? If I ask you to divide that into 3 groups, you can just say, oh, I'm throw half of them out and only divide 1/2. Because otherwise you can say, oh, I'm just not gonna do anything, and there are 22 remainders. That's gonna be ridiculous. So we have to impose an extra requirement, which is that the remainder needs to be between 0 and n-1. If you think about it in math terms, usually you see that as like q is between 0 and n-1. That might seem weird, like why do we need that? But again, if you think it intuitively, if there are, let's say if there are 3 more objects here, then you should divide them. You can still divide them. You shouldn't keep it. You shouldn't keep them as remainders. There are more than n. That means you can still divide them. You can still put them into groups. So you should divide until you have less than n objects. This means it is less than n. So it's less than or equals to n-1. And also you should, when you divide, the remainder should be 0 or positive. It makes no sense to have a remainder of -3, for instance. But you can say, oh, I divide 22 objects into 3 groups. So I have, each group has 8 objects, and then I have -2 remainder. Which kind of works, right, visually. So you kind of like, I borrow 2 balls from my friends and put them into the group so I can happily divide them equally. So it works in some sense, but for this topic, when you talk about remainder, then we don't allow negative numbers. You can borrow things. You can only arrange what you have. So if you have 22 objects, just deal with those 22 and see how many objects you have left. But that's the intuition behind this. And the way we write it is we write it as m equals to r times n. That's the square. That's the number of objects we successfully divide. Q is what left over on the other side. We can write it as n times r. I think maybe some textbook does that, but as long as you have Q in the back, then we are good to go. We call R the quotient. We divide this quotient between the two numbers. Or some kind of ratio, but not exactly ratio. And Q is a remainder, what remains after we divide them. And yeah, some notes that if Q is 0, if there is nothing left over, that means we divide everything in group of equal size, and that means we have m equals to r times n. In this case, if you go back 5 minutes, you will see that this is what we mean to be divisible by a number. So that's the idea behind this. Oh, yeah. Let's discuss that later. Oh yeah, some example. So there are pairs of numbers. You want to express them in terms of quotient and remainder. Let's start from A. It's 10 and 4. Maybe it's useful to just do it by hand, just write them out at first, because you can see that the numbers it shows are small. So we start from 10 objects, equals to 10. Then we want to divide it into 4 groups. So you can do 1, 2, 3, 4, 1, 2, 3, 4. We have 2 left over. So each group has 2 elements, and the leftover or the remainder is 2. So that means we can write 10 as 4 times 2. We have 4 groups, each group has 2 elements, and the remainder is 2. That's simple. And hopefully in the future, like an hour from now, we can build upon this concept. So let's go to B. Let's go in the order on this page. M is 19 and N is 3. So again, think of 19 objects and you arrange them into 3 rows. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then this one, that's ball. So each group has, 6 objects? Then it has 1 left over. So that means you can write 19 as 3 times 6 plus 1. That's 19 for you. Explain visually, quote unquote. Next, we have m equals to 15 and n equals to 2. You might be able to see something here, right? Oh, if you divide that into three groups or 3 rows, just do it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, nothing is left over. Nice. That means the remainder is 0. That means 15 equals to 3 times, forgot that, each row has 5 balls, so 3 times 5, and then plus 0. Most of the time, you don't write 0. If you know, oh, they are 15 is divisible by 3, just ignore them. But just for now, just for this topic, you should also write that's plus 0 to say that, oh, these are all in the same format. And lastly, this is weird. You might say, oh, everything is easy, but what's about the last one? If you have 5 rows, there are 5 rows. You have nothing to arrange. How do you arrange? It don't arrange anything, right? There's nothing to do. Each group, you can divide 0 objects into 5 groups. In each group, you're gonna have 0 object. So that works. What about quotient? Sorry, what about the remainder? So the quotient is 0. Remainder? 0. That means 0 is what? 3 times 0 plus 0. Weird, right? It looks very weird, but that's how we divide. 0 equals to 3 times 0 plus 0. Yes, you can divide 0 objects into 3 groups of equal size. Each group has 0 object. Yeah, it's weird, but the thing about this is it's weird, but once we have that, once we have a way to deal with all the numbers, then we can use the definition. Like in this case, you would say that 0 divides 3. By the definition. Oh, sorry, 3 divides 0. 3 divides 0. 0 is divisible by 3. So if you have, an argument with your friend, whether you can divide 0 by anything, then the answer is yes. You can divide 0 by anything. If you want to divide 0 by 100, you want to make 100 boxes, and you put 0 object in each box, you get 0 at the end. That's the this is the divisibility and remainder. Okay, what's next? Oh yeah, and for should I put it here? But if you get caught, or if you see some fancy notation, there's a notation in this case called a mod. We also gonna study this in a moment, but for now you can mod a number and the result. You can mod a number. In this case, what? M by n. You have the same m and n. And the result we get is the remainder, which is q. We rarely write that. If you put that into a computer or a calculator or code, then that should work everywhere. N is q. Is a remainder after you try to divide m by n. Okay, that's the first ones. Next we have the concept of prime. Right, before you can know prime, you have to know what it means to divide. So here, give me a moment. Okay, let's continue. Next, before we know prime, we have to know the concept of divisibility. Whether something divides something else. And then if you have lots of numbers, you can have fun. Try sounds. If I give you 2 numbers, m and n, you can just do it. Just try. Okay, can you divide 19 into 3 groups? You can or you cannot. That's an easy question. The more difficult question is if I ask you, can you divide 19 by anything? If I only give you a number m and ask you, can you find a number that divides that number? Then you have to try lots of numbers before you can finally see if you can or cannot. You have to try all the numbers like 2, 3, 4, 5, 6, 7, and so on and so forth. But that takes some time. That's the reason why prime is difficult. That's the concept. Right, so some numbers are sometimes if I give you a number like 19, then if you try all the numbers, all the number ends, as the smaller numbers, you cannot divide them in any way. But like if I give you number 51, then it takes you some time to see, oh no. Let's say numbers like 199. That's a pretty big number. Oh wait, maybe not that. I'm not sure about that. 299? And then there's another number that looks difficult to find, but you can actually find.
It's 17 times.
Sorry, I'm not prepared. But yeah, let's try like 1001. Interestingly, you can divide that. You can divide n. You can divide that by n. Of course, you can try that. Use your favorite calculator. You should get something like 143. That means there's some smaller number that divides that number. So the process kind of not deterministic. It's mostly random, I would say. Sometimes you can, sometimes you can. So we divide numbers into two groups. We have a prime number. It's a number that you cannot find any smaller numbers that divides it. Besides 1 and itself. Besides 1 and itself. Because if I give you 19, you can say, oh, I can divide it by 1. Let's just put everything in a single row. That works, right? So it's 19 times 1. That works, but that's not actually what we want. Hopefully. But then we have... we also have 19. It also works. If you have 19 objects and you want to divide it into 19 rows, sure, you can divide it. You're gonna get a long, a tall column. There's only a single object. So this is what we math people call trivial. This always happens. We don't care about trivial numbers. It's too easy, it's too obvious that this works. So we say, yeah, every number has this property. It is divisible by 1 and it's divisible by itself. So when we reply prime, we have to, exclude those two numbers out. That's the property of a prime number. And if it's not a prime number, we call it a composite number. Compose. You compose music. You assemble lots of notes into a nice arrangement. And you combine things. So that's two more words. You could, or you might. And yeah, there's a fun fact about prime numbers, which is that 1 isn't a prime number. It's kind of weird. Like usually when you think about prime number, oh, it's divided by 1 in itself. But the thing is like 1 and is, since 1 is 1, itself is 1. So there are two. There's only one divisor, not 2. That's 1 equals to 1 times 1? Oh, just 1. But there's only one way to express 1, which is just 1. It only has one divisor, not 2. So we exclude that. And actually we have a better reason to exclude that from the prime number. We will see in a moment. But yeah, there's a new definition. Here, let's see. So there are 3 numbers on the screen and your job is to determine whether it's prime or not. Let's start with 20. Is 20 a prime number? Guess not, right? 4 times 5? Oh, someone might say, oh, it's actually 2 times 10. Again, you are both correct. Like there could be more than one way to express a number as a product of two. But, all you need is just a single example. Okay, you can write, you can express a number as a product of two numbers that are not itself and one. Because again, this you can write this, but that doesn't prove that it's prime. It's correct, but it doesn't prove the point. You can choose 4 times 5 or 2 times 10. For B, 39. That might take you sometimes. If you have enough times. But maybe you use a calculator or math helper, or the app that I recommend in the first class, which is called Socratic Math Helper, or Photomath, I think. That's another popular one. 39 can be factored as 3 times 13. You can guess it yourself. 3 times 13 is 39. Oh yeah, I should also write it. Okay, in the first example, this is a composite. So it's B. Very simple enough. To prove a number is a composite number, just express them as a product of two numbers. What about prime? Can be see, for 29. Is that a composite number? Maybe you don't know. You have to try 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, all the way up to 28. That's gonna take some time, right? Eventually, you would find out that 29 is actually a prime. It's a prime number. Because we cannot divide by 2, 3, 4, all the way up to 28. Maybe try all the numbers and that's the way to divide them. You can see that there's a huge difference, right? To prove something is a composite, you only need to give a single example. To show that something is a prime, you have to do it. You have to try all of them. Show that it's not a composite number. So that's the nuance. That's why prime is difficult. Yeah, there are some nice theorems or some nice facts, I guess, to help you guess or prove that a number is a prime or not. One nice theorem, which again I'm not gonna focus on here. Just saying, is that instead of testing up to 28, in this case we have to test all the numbers, right? But instead of testing up to the 28, you can notice that 28 it is not gonna be the case that 28 divides 29. If you have 29 dots and you arrange them into 28 rows, right, then that's not gonna work, right? Because there are too many rows. There's gonna be some leftover anyway. So in this case, it is obvious, quote unquote, that 28 is never gonna divide 29. Because if each row has one object, then there are 28 plus a remainder. But if there are two rows, then you have on what? 28 times 2. That's 56 already. So it is impossible to divide 29 into 28 equal groups, 28 groups of equal size. But maybe, maybe what about 13? Maybe that seems, oh yeah, 13 seems possible. But again, there's some interesting argument which I don't have time to go over, but the theorem or the trick is that you only have to trace up to square root of that number. In this case, it's square root of 29, which is about 5 each. So in this case, to test or to prove that 29 is a prime, all you need to do is to test numbers from 2, 3, 4, and 5. That's good enough. Only 4 numbers. You don't have to care about 6, 7, 8, and so on up to 28. A short or a quick reasoning why we only need to test up to square root of that number is that suppose that we have let's think about 28 for instance. You can divide into 4 groups, right? Each group has 7 dots. 4 times 7, so 4 divides 28. You can also divide it into 7 groups of 4 dots because it is because they are symmetric. You can kind of, flip one group to another. You may notice that if you can divide that by 7, then the number here, the number 4 here, is also divisible by. The number 4 also divides 28. If 7 divides 28, then 4 also divides 28. So that means if you test 7 and you get the result 4, then you should have found 4 already. If you test from 2, 3, 4, 5, 6, and so on. And so on. The 7 is large enough that if it happens to be a factor, or if it happens to divide 28, then the number of, there's a smaller number somewhere that divides 28 too. The product of the two numbers is 28. So that's it suffices to, you don't have to check up to 7, and that's already too large. So that's kind of like the middle point, like the square. Oh, if you test up to here and you see nothing, then you're not gonna see anything beyond that, because it would have appeared before already. And again, that's some fun trick about. Oh yeah, that's the first one. Yeah, and the second one is there are some nice helpers or tricks again. And to test whether something is divisible by 2, to test whether something is divisible by 3 and by 4 and by 5. And you have seen that, you have seen all those tricks before. For something to be divisible by 2, the last digit has to be even. Or the number itself is an even number. If it's even, then it's divisible by 2, which is actually how it's defined. So it doesn't help much. But like for 5, if a number is divisible by 5, then the last digit is 0 or 5. We have 5, 10, 15, 20, 25, 30, and so on. Those are the numbers. Divisible by 5. All you need to check is the last digit. And for 4, you cannot check the last 2 digits. You can see if those 2 digits divisible by 4. If you want to see if 1, 2, 4, 3, 2 is divisible by 4, all you need to check is the last 2 digits, which is 32. If 32 divisible by 4, yes. That's right. You can write them as 4 times 8. Yes. That's green. And that's 4 times 8. So that means the larger number, the 12,432, is also divisible by 4. There are more tricks there. And actually there was a clip from number 5 that was just uploaded 2 days ago. Kind of a coincidence. If you have time, I suggest you go watch them. And okay, but let us finish this part. And so we talk about divisibility, remainder, prime, composite. Next concept is This is a pretty fancy way of saying theorem, but again, it's actually intuitive. If there's a natural number n, be expressed as a product of prime powers. So if you write if you want to write 12, you can write it as 6 times 4, or 3 times 4, or 4 times 3, or 12 times 1. There are more than one way to express 12 as product of numbers. But to write it as a product of prime powers, not just numbers, but those numbers have to be prime. And prime powers mean it's a prime to some number. If you enforce that requirement, then there's only one way to express any number, any natural number. And for instance, if you come back to 12, you say, oh, okay, 12. So 12, 10 ways to, actually like 6 ways to express them. But if you have to express them as prime powers, so it's 2 times 2 times 3. Now these 3 numbers are all prime. Then you have to, if you have to express them as a power, so you will need to combine 2 and 2 to 2 to the 2, and then times 3. So that's how you express 12 as prime powers. 2 to the power of 2, 3 to the power of nothing, 1. Product nothing is 1. So that's a theorem, but there's only one way to express it in this form. Unless you could swap, but that's kind of it's required that if you arrange them from, let's say, smallest to largest, it's unique. And once we have this unique representation, then you can define things. And things would be simpler sometimes. For instance, for example, actually you see the number is in the example. So 12 is 2. Oh, by the way, if you use, scratch paper, then maybe you could start from what you know, which is, just write it as 2 times 6. And then, what about 6? 6 is not prime, it's a composite. So, but we want it to be prime powers. So that means we have to first divide the number 6 into smaller numbers, the product of smaller numbers. So it becomes 2 times 3. Now we have 2 times 2 times 3. And then you can write as 2 square times 3. That's how you do it, one step at a time, by hand. But of course, if you use an app or something, it will give you the answer immediately. It's convenient, but what about 40? 40 is 5 times 8. And then what about 5 is a prime number. You have 5 objects, you can divide it by 2 or 3 or 4, so it's a prime. What about 8? That seems even, so it's a prime. So it's 2 times 4. And maybe we are done, but actually 4 is 2 times 2, so you have 2 also. Subdivide it. Or maybe I should also write some lines. Now we have 5 times 2 times 2 times 2. And if you rearrange it from, let's say, lowest to largest, we have 2 to the third times 5. That's how we express 40 as a product of prime powers. And then for C we have 220, 210. And this one may, take some time. It's 20 times 10. 20 is 7 times 3. And then it's 2 times 5. And then you take a look at 2, 3, 5, 7, and you see that they are all primes. So you just rearrange them from smallest to highest to make it look nice and easy to find. And that's all. That's the best you can do. They are all powers. Power of 1. Lastly, we have 256. It's gonna take some time to find the factors, but again, if you have attentive enough, okay, it's 2 times 128. 128 is 2 times 64. 64 is 2 times 32. So on and so forth. But eventually, if you are lucky, you should get 2 to the 8. 7. Yeah, 8. Did you write 7 on BB8? Anyway, so that's prime powers. Once you have, this unique representation, then you can plug the numbers you got into, machines or other formulas in the future. So that's that. Oh, and finally, just these are not like the formal definition, but you might see them somewhere in kind of problems or fun, recreational problems. So we have a word like square and cube. Square is a square, cube is a cube. If you think about of them as objects. But yeah, they are kind of the same. The square means if they have 2 equal sides, and the area of that square is called square. And similarly, if you have a cube, and each of those sides are the same length, then the value of the cube is the cube of that number. Not surprisingly, like I think there was square and cube came first, and before mathematicians use forum or studium to define numbers. So yeah, if a number is a square, then we can write it as something else square. If a number is a cube, then we can write that as a cube. Understand if we ask you, is 25 a square? Square? You will say yes, because 25 is 5 square. That's simple. Is 3 a square? No. Because, so kind of explain why, but yeah, just for now. If it's obvious, it's obvious. So it's not if it is a square. No, it's not. And then same as Q. If I ask you is H a Q? Then yes, because my head is because you can write X as something else to the power of to the third power or something else Q. Or in other words, you can make a cube of value H. Each side has length 2. The value is 8. So H is a cube of something else. So that's that. Again, not a serious definition, but I see it somewhere. And lastly, and this is more common. For square and cube, you have a number that you have a kind of a variable or a number below, and then you have a number on top. And for the power of k, that's the other way around. You have a number. You are given a number at the bottom or at the base, and then the power is, any other number. So for this definition, the n is a power of k. It means we can write n as k to some power. K to some power means it's the power of k. Again, kind of, the duality between divisible and divisible, divides and divisible. So you can write n as k to the power of something. So it's the power of k. So 16 is the power of 2 because 16 is 2 to the 4. 16 is also a power of 4 because it's 4 to the power of 2. In this case, it's 4 squared. And lastly, 243. It's not common, but again, if you play with numbers long enough, you will be able to recognize that on the fly that, oh, it's a power of 3 because it's 3 to the 5th. And yeah, that's all for the tour of some keywords when you play around with numbers. There's one short exercise, which is kind of, one of each topic. So we have, first we have the usual remainder one, m equals to n times r plus q. Then we have prime powers, express a number as a product of prime powers. And then we have by trials and errors. This means that there's no method or there's no fixed algorithm to solve these two problems. Just try things. Can you express 52 as a sum of a square and a cube? And a cube. And then you have to go back, to see what is a square and what's a cube. And lastly, again by trial and error, express 25 as a power of 2 and a power of 3. That is for the second section.